Like Greg said, I'm with the North Carolina Geological Survey. We've been around since 1823, so I even predate the folks that were here in 1916 a little bit. But we've been involved in studying landslides in western North Carolina. So my talk's kind of bridge some of the research, looking into what those conditions were, where we've seen those in the past, and then some of the mapping analysis we've done to help provide tools to decision makers, homeowners, to number one, anticipate when these events might happen, and then be aware of surroundings and places that might be problem areas to help identify those on the ground. So the information that I'm going to present has have been gathered over this time frame from about 2003 to the present. The bulk of the work was done between 2005 and 2011 when we were doing landslide hazard mapping county by county. So in that time frame, we completed mapping of 4 counties. We started with Macon, and then did Watauga County, then Buncombe, and then Henderson County, of those counties that we were actually completed. And as part of these studies that we've done, including a geologic and geohazards assessment along the North Carolina section of the Blue Ridge Parkway, we've created a landslide geodatabase. So we're documenting present and past events. So part of what we're doing, I guess, is creating a geospatial legacy of events that have happened in the recent past, and trying to go back as far as we can and document things that have happened on the ground going back to 1940 and 1916 to start building a picture of those events through time. The mapping we did ended in 2011, but there's work that are being done in watersheds in Jackson County and have been completed in Haywood County by a private firm, Appalachian Landslide Consultants. Those are a couple of folks that used to be on the landslide hazard mapping team, and so they've been able to get some funding to continue that work sort of at the watershed level. So just to give you a broad picture of the impacts of landslides in the past, since 1916, we've been able to document there have been at least 48 landslide-related fatalities in western North Carolina. Not a lot, but I think my former boss, Jim Simons, the state geologist, put it very well. 1 is too many. And 7 of the fatalities and 5 serious injuries have been since 1990. There have been 43 homes destroyed or condemned from landslides. This is not flooding. And that's mainly since 1990. 4 other buildings have been destroyed. And one of them was a small building, probably about 1/10 the size of this room, but it was an important building because it was the chlorinator building for the Bryson City Municipal Water System. So when that landslide took out that building, that town was out of water for I don't know how many days. So, a small landslide in one area can have a big impact, we found. And there have been about 41 homes damaged since then. So it's a relevant and important problem, and it's one that we can actually do a lot to, one, mitigate and understand, and then improve our track record on either building better and in the right places, and being smarter about how we do development. So this is a version of the chart that Jim showed earlier, and it shows time in this axis and rainfall here. And what I've added since then is I've tried to come up with an estimate for some of these past events for the actual numbers of landslides that these individual storms have triggered. And that's the top bar here. And what we found in our research and looking at the amounts of rainfall, typically when you get over 5 inches in 24 hours, that's kind of a threshold when you can expect to see landslides occur, 5 inches of rainfall. And that's actually a work that was done back in the 1970s. But the data that we've compiled sort of falls into that category. But one thing we're going to look at when we get beyond total rainfall, it's actually what's probably a better indicator is rainfall intensity and duration. So if you get, 22 inches of rainfall in 24 hours, like the 1916 storm, that's pretty intense rainfall. That's pretty close to 1 inch per hour for 24 hours. So that's going to have a big impact. So there were probably thousands of landslides in western North Carolina from that particular storm. And as pointed out earlier, that scenario is also very important because there's an early July storm, the back-to-back storm scenario. In fact, if you look at western North Carolina, that scenario where the storms are about 6 to 20 days apart, that's on average, that's about every 29 years for all of western North Carolina. So that happened in 1916, 1940, not storms that affected this area so much, but other parts of the state, and then again in 2004. And so in looking at how often we can expect these, you can look at the numbers in a variety of different ways. For all of western North Carolina, since 1916 to 2013, last year when we had a lot of heavy rainfall, a lot of landslides and flooding, it's about a storm every 19 to 20 years on average. If you just look at Asheville and Buncombe County, from 1916 to 2004, the three major storms, and those are storms that have triggered hundreds or maybe even thousands of debris flows. That's about every 28 years. If you throw 2013, that period of time between January and July where we had a record above average rainfall, is one of those long drawn out events, it's about every 24 years. So, the point is, yes, we need to plan and think that this is going to be a recurring pattern, and it's probably not going to stop anytime soon. And just hope we're a little bit more prepared for the next go around. So one of the things that we've done in mapping out for western North Carolina, all these colored lines and polygons indicate those general areas that have had landslides related to these different storms. And going back to 1916, these are the red areas here that are outlined where we've taken newspaper accounts and general reports from the Southern Railway wrote a great book about the effects of that storm on the railroad. And so you can see, they pretty much follow all along all of western North Carolina, all up along the Blue Ridge Front or the Blue Ridge Escarpment. The 1940 storm here, the first one in mid-August, that's Watauga County, and it's actually enlarged a little bit. That storm triggered over 2,000 debris flows in Watauga County alone from that individual storm. And to put that in perspective with Francis and Ivan, from what we know, all throughout western North Carolina, there were about 400 landslides. I'm sure there were more, but what we've got documented or have good evidence that those occurred. Those two storms produced 400 or so, probably less than 1,000. So the takeaway lesson from that is, 2004 was pretty bad. It could be worse. It could be a lot worse. So this is one of the counties where we did landslide hazard mapping. So that's one of the reasons there's a lot of concentrated dots there. So the blue dots are actually those landslides that we looked at and did some investigation on in 2013. And those investigations, we're not doing landslide hazard mapping anymore, but we get requests for technical assistance, either from emergency management, municipalities, homeowners, engineering firms. And so that data goes into the database. And so we try to get learn from what happened in those events to help us plan and understand what went wrong. I guess the point of this diagram here is that if you live in the mountainous area of western North Carolina, sooner or later your number's probably going to come up, in terms of landslides, if you take the long view perspective. So in mapping landslides and recognizing where it's happened before, because that's important, what we find is that the modern landslides tend to happen in the same general areas where the past landslides have. So in the process of mapping and identifying those, we can get at least an increment closer to understanding where they might actually happen. So if we look at this cartoon model of where a debris flow starts, and that's a mudslide or mud flow or terms you typically hear, that's the most frequent, most damaging type of landslide that we have here in western North Carolina. And they are triggered by a heavy rainfall event. And usually they start somewhere on a steep hillside in this concavity in the hillside, a feature we call a colluvial hollow, and they travel down the drainage, and this material accumulates at the toe of the slope in a feature we call a debris fan. And that's a very typical landform that we see here in western North Carolina. So here's a oblique photograph view of one of these. This is the debris fan right here. And this large area up here, there's probably small colluvial hollows within this much bigger feature. But basically all this material used to be up here. And so when it comes down the hill, it accumulates in this broad feature here we call a debris fan. And they're fairly popular places to build on. One, the slope is fairly low. You're not excavating bedrock. You are out of the floodplain. So I mean, there are advantages to that. And so what this means is if we have future debris flow activity that initiates up here, it's probably going to end up somewhere down here. So this would be probably the worst place to build at that choke point right there, because everything's probably going to come down through here. If you're way out here on the top, your chances are significantly improved. But it's something I think it's good to know about before getting yourself into some of these situations. And so these old deposits that we see down here have been here for a long, long time. And in fact, some of them dated in Watauga County go back to when the magnetic poles were reversed. So that puts it somewhere 780,000 years ago. And some recent dating puts it at about 1.5 million. So this is not a new phenomena here in the mountains. And we look at some of the debris flows that occurred in Macon County and Francis and Ivan on Wye Creek, where they cleaned out the channel. You can actually see 3, 4 sequences of earlier debris flow deposits that predated the one in 2004 up here, number 5. So, you know, these are areas where these kinds of things recur over geologic time. So that's part of the, you know, from our human standpoint, trying to grapple with when and where these happens is we're talking about a little bit of a different time frame, a different time perspective here. So in Francis and Ivan, I don't recall that there were many landslides actually in Asheville. There probably were some, but the biggest one in the nearby area was at Stearns Cove out towards Inca. And the debris flow destroyed this house right here. And this is upstream from the house. So this is the path of the debris flow. This is the mud line in the tree right here. And that Rebecca, one of the geologists that worked for us then, is about 5'6". So you can see that, you know, that's probably getting close to 30 feet up that tree. And that point is right here. The house is right here. So in the course of doing the landslide hazard mapping in Buncombe County after this event, we identified that this area down here, these areas that are tan are old debris flow deposits from those debris fans like I showed you earlier. And these yellow outlines are actually the tracks of those 5 debris flows or 4 that coalesced and caused this damage. So that same pattern is modern landslides tend to occur and affect similar areas that they have in the past. And looking at the stability index map, which is part of the landslide hazard mapping, which shows those areas that are more prone to this type of landslide, with the red areas and the purple areas on the little chart here and on the map here, those are the places where they're most likely to start in these major storm events where we have 5 inches or more rainfall in 24 hours. And so when we calibrate this model, we are not calibrating it to these points. We calibrate it to points where debris flows occurred on natural slopes, because these were all failures of embankments. So it's not that mobilized into a debris flow. So it's where in road building, material been taken out of the hill and put on the downhill side. And it's not that you can't do that. It's a very common practice, but there are good ways to do that and there are not so good ways to do that. And so what this map does point out, even though it's not designed to depict those areas where you're going to have problems with modified slopes, it points out on the natural slope where things are marginally stable as it is. So if we go in and do something that tips those scales a little further towards unstable, we can be building in problems for ourselves and the people downstream. So in looking at how rainfall, which is the principal trigger for debris flow events here, and I want to make a distinction between the trigger and the causes, because, you know, I think the way the biologists look at it, you have predisposing factors, things that predispose a certain circumstance, situation, organism to problems, and so that would be a cause in the geologics way of looking at things. You have certain topography, certain soil types, certain bedrock orientations that all predispose an area to debris flows. And what sets it off is the rainfall when it infiltrates through the soil and it hits something like bedrock here. And this usually is fairly shallow, less than 6 feet deep in a lot of cases. And that shallow water table builds up at the top of bedrock, overcomes the shear strength of the soil, and it takes off down the hill. And when there's enough moisture, it actually liquefies. And it goes down the hill, has a snowball effect in training more material as it goes down the hill. And that's kind of what happened at Peaks Creek, the one that was mentioned earlier. This is where it initiated on Fishhawk Mountain. This is the path. Again, switching to the time frame aspect. This is a home that was destroyed. You can't see it here, but it's been pushed about 6 or 10 feet off its foundation and kind of leaning. The floors are buckled. On September 15th, the conversation could have gone something like this, because Mrs. Treadwell had lived there, and she had bought it, and that house had been there for 100 years. Why there hasn't been a landslide here for 100 years? You know, well, that all changed on September 16th. And so, as it turns out, this house was built in the bend in the channel where landslides have deposited material over geologic time. And that bend in the channel is where they go around the corner and they bank, and they can overtop that hillside and impact areas outside of the channelway. So at this spot right here, our calculations were that this debris flow was traveling about 33 miles an hour with a discharge of about 40, but probably closer to 70,000 cubic feet per second. That's a lot. The French Broad River, 100-year flood at Asheville, I think the discharge is something on the order of 40,000 CFS, something like that. So fortunately, this is concentrated in a fairly small area, and they can move boulders that are about 16 tons. And you can see how they're stacked up there, piggyback style. That happens in modern debris flows, and that's a typical thing you can see in ancient debris flow deposits. So these things are actually pretty easy to recognize on the ground. So every now and then we get the rare chance to look inside of one of these colluvial hollows. So there are advantages to landslides. It takes the stuff out of the way that we normally can't see and only can imagine using a lot of imagination. So if you look at this slope here, this is the concave slope on the ground surface. It's often very gentle. And in this case, this red line separates what is embankment or fill that's above the native soil here, which we call colluvium. And that colluvium is stuff that's accumulated in this low spot that's created by this intersecting network of fractures and layers in the bedrock that makes a little trough in the hillside. So these hollows are there are because of the structures in the bedrock. So that has a way of, controlling where these low spots are, that soil, and when we have rainfall events and moisture, they accumulate and you reach a critical thickness of soil and a critical rainfall amount, and they fail. And so over geologic time, it's a cyclical thing. You get to that critical point, it fails, it empties out, and the process starts to refill. So the conversation could have gone something like this on January the 2nd. We had the opportunity to do some carbon-14 dating of these colluvial units in here. And so you can say, well, I've been here 4,000 years and there hasn't been a landslide. Because that's the age of those older deposits in the bottom of that hollow. So there's a long residence time for some of this stuff on the hillsides before it fails. And that's the trick. Which one is going to go next? And that's a problem. But if we add fill material to these without the right engineering, we're actually accelerating that process. We're taking material and loading that hollow at a rate faster than it would under natural conditions. So we may be increasing the recurrence interval of that. So there are lots, you can do an engineered fill on this and actually improve the stability of that. But if the engineering with the right grubbing and drainage and compaction isn't done, then you can be making the situation worse. And oh, by the way, this is the house that was hit by the debris flow right there. It was basically turned into a pile of sticks. So you don't need a 2¼ mile long debris flow like Peaks Creek to completely destroy a house here. So those folks, believe it or not, survived that with only minor injuries. They were in that house. The roof is about 150 feet downslope from where the house was. So I'd say they're pretty lucky. So, we've heard about and we've talked about these big storms and tropical systems that trigger debris flows. We learned in 2013 we don't need those. We can have that with record rainfall event and then storms embedded within that record rainfall. So this is a great graph that the folks in Greenville-Spartanburg National Weather Service produced that shows what the average rainfall is, and everything in dark green is above average. So this is for the period from about mid-January 2013 to July, when we had these storms, these little steps in this graph here of cumulative rainfall, when we had these storms embedded within this period of above average rainfall. So you have that high antecedent moisture conditions and storms, and each one of these red arrows are when we had documented landslide events related to these storms. So this was a very important one here in Asheville. This is the house up on Black Oak near Beaver Dam that the failed, and we'll talk a little bit about that later. So there was, 3 of these events were federally declared disasters for flooding and landslides. So you can think of this as sort of a, period of time where there were over 300 landslides in western North Carolina, comparable to Francis and Ivan, but this was spread out over, a 6-7 month period. So this is another weather scenario where we can expect to have problems. So we're not doing landslide hazard mapping anymore, but what we are able to do is when we get requests for assistance in landslide events, then we, whether that's from a homeowner or an agency, an engineering firm or whatever, we can go out and collect the basic information and try to answer some of the questions. What happened? Is it still moving? Is it safe? What are the long-term prospects? And give some general guidance on, what that person or municipality can do. And then also as part of that, document what's going on and get it into the database. So this is an example of a home in Buncombe County. And this is a scarp, a crack in a landslide. So this is not a debris flow. This is a different type. And this actually, one of the reasons we map these debris deposits, and that's what's shown here in tan, superimposed on an aerial photograph from the Buncombe County landslide hazard maps. They show us where landslides have deposited material in the past, but they're also thick accumulations of unsorted, unconsolidated, not really strong material. So when they get to a critical thickness, sometimes they can start to move again in a slow-moving landslide. So over a period of about 6 or 7 months, this landslide had moved about 20 feet and was going right through his house. And so what was fortunate for this fellow, he had enough property where he could pick up his house and move it off the landslide. Most of us don't have that luxury. It's not a luxury for this fellow. Don't let me give you the wrong idea. This was a long, drawn-out, expensive, and heart-wrenching, gut-wrenching experience for this family. And part of it is, understanding what you're building on, and then what you do on those slopes. Because, if these things are marginally stable, and some are very stable, but it's knowing the specific conditions, where you put fills, where you put septic tanks, where you direct water, all influences on how this slope is going to behave. And so going back to 2013, looking at, okay, one of the things we want to do, where we have landslide hazard mapping, how close is it? Because, it's a model. It's designed to show, where are these areas where we expect problems. It's not going to say in the red they're going to be landslides. I think what we say, well, I know what we say is if these red areas, if there are landslides, they're probably going to happen in these areas. So this is the embankment failure on Vance Road. You can see the bedrock here, and all this material out in this area that used to be around here was the fill material that's part of that road. And you can see the layering in the bedrock's kind of tilted here in that direction. Makes a nice sliding board or a slip plane. So this is where that point is on the landslide hazard maps, right in the middle of that big red area right there. So if you're looking for areas where you might anticipate problems, the map is a general guide. These red areas, particularly where the roads cross them and things like that, if you're trying to get a leg up on anticipating where you might have problems, this is one of the tools that are out there now. So the maps can be misleading, like any other map. And so this is the site where the house failed in Beaver Dam. And you can see the cracks in the landslide and the front end of the house dropping down. And this is one that had to be demolished. This is the landslide hazard map. So you can see this is the drainage coming up here. And it's very red and very steep on either side of that. When we get up here at the top, you're in the low hazard zone here. And this is a slope map, because this map, one of the factors that goes into making it is slope. And that's an important aspect of that. There's other factors, but slope is key. And you can see the slope where the house is, it's actually, pretty flat in this range. So when we see landslides, we typically think they're going to be on ground steeper than 21 degrees, so down in this range. So what's going on here? Well, as it turns out, the LIDAR was an important tool in making the slope map. The LIDAR was flown after this house pad was built, before the house was built. So what we think happened here, and looking at this, the reason it's flat is because it was filled in to make a house pad, right? And so if you just look at the slope map or the stability index map and say, oh, I'm on a red pixel, I'm fine, or I'm not fine, or I'm in the green, I'm fine, I encourage you to kind of zoom out and look a little bit at the bigger picture, because looking at the landform, this is actually one of those colluvial hollows that have been modified and filled in. Great view for that house, but that's about, I don't know what the market value is for that. It's probably getting close to $500,000 that no landslide insurance, and I think the owner signed it over to the county had to demolish it. So we all have some skin in the game if we pay taxes, right? So that's how, even though you might not be directly affected, this is something important that we need to consider. So when we're looking at the amount of rainfall it takes to trigger landslides, one thing that I talked about is the rainfall intensity and duration, how hard it rains for how long. So this is rainfall in inches per hour here, and this is the number of hours. And so if you look at Francis and Ivan for the Peaks Creek debris flow, and remember hurricane, that happened in Ivan and Francis came before, so things were already pretty wet. That rainfall was about an inch per hour for a little over 4.5 hours that led up to the Peaks Creek debris flow. So that's one point on the graph. And so that general rainfall intensity, if you extrapolate that over a much broader area, which is not a good idea, but that resulted in about 400 landslides or more in western North Carolina. Watauga County, the reports for that 1940 storm, it was about 1 3/4 inches per hour for 6 hours, okay? And so that resulted in Watauga County of about 2,100 debris flows. And I'm guessing that over western North Carolina, that was probably more like 3,000. The big storm was Camille, Nelson County in 1969. Hurricane Camille tracked over there. It was 3.5 inches per hour for 8 hours, and that triggered over 3,700 debris flows. So this is that same thing shown in a chart view. So this is where we have points that show debris flows occurred on unmodified slopes. This is where that rainfall intensity where they've occurred on slopes that have been modified. So when we modify slopes, we can actually tip the scales to the point where it takes less rainfall to trigger these debris flows. What we're doing now, studies to get monitoring in the ground to get a better understanding of moisture in the ground as it relates to rainfall. So we have stations at Bent Creek, Poplar Cove, and Coweta. I'm going to wrap up really quick with findings and conclusions here. So recurring weather patterns, we can expect this to happen again. Debris flows are the most widespread and most frequent. But if we have a rock slide on I-40, that single landslide probably has the biggest economic impact, particularly if you're a business in Asheville and you need to get goods west or you need to get something from the west here. So those are big ones too. So the question for these events is it's not if but when, okay? So in looking forward to the climate change scenarios, rainfall intensity and duration is critical to a landslide occurrence. And if we see an increase in the frequency of high intensity storms or an increase in the intensity of those storms, we can expect an increase in landslide occurrence. So let's see. So basically, the landslide hazard maps are a tool out there that can be used. So whether you're a homeowner, a business, or whatever, they can give you an idea where these potential problems are. And so because what we do and where we build and how we build can result in damage, that means we can do something about it. That means we're not necessarily at the mercy of nature. We're not necessarily say it's going to be a big rainfall event and throw up our hands and say there's nothing we can do about it. So yeah, what I'm saying is, yes, there are things that we can do to improve where we build, how we build, and anticipating these storms. And so to wrap it all up, it's watch where you build, watch how you build, be aware of your surroundings uphill and downhill, because if you're on a hillside, you're all connected. What somebody does upslope may influence you down here. What you do down here may influence somebody up there. And anticipate these rainfall events. Like Jerry said, be prepared, know how to get out. If your road is blocked in a landslide, do you have a way to get out some other way? And so I've gone over a little bit, but I want to make one acknowledgement. So the work that I presented here really wouldn't have been possible without the work that these folks did from 2005 to 2011. That's Team Slide, and we've had a lot of other help. So I know questions are going to come later, but thanks. I appreciate the opportunity to speak here.